Swayam Prabha. Digital India. Educated India.
Good morning. So I'll be doing some 3-4 problems in this class. The problem sheet is uploaded in Moodle. If you want, you can download it from Moodle, and I will also project the problem here though. So these problems are related to batch distillation or differential distillation as well as differential condensation. And the problems are selected such a way that we go from very simple, easy to do to little bit complicated. Okay. So take a minute to read this problem. So here we are dealing with binary mixture of ethanol and water, and ethanol is species A and water is species B, because we know ethanol is more volatile than water. So the initial charge is given 100 moles of liquid containing 18 mole percent of ethanol, and the mixture must be reduced to a maximum ethanol concentration in the still of 6 mole percent. Okay, so that means let's say you start with the distillation column, and this initially contains 100 moles with mole fraction XF of 0.18, and you want to do differential distillation to get a liquid mixture such that here XW should be 0.06. So the question is to calculate the moles of liquid present. So we don't know how much moles of liquid is present here at the end of the operation, and the composition of the composite distillate. So here you might have collected the vapor, condensed it, and then you would have collected all the vapor into a receiver. So this is the distillate D. We need to find what is D, and we need to find what is the average distillate composition. So these are the questions to be asked. It is usually a good practice to draw a schematic of the problem statement and then give the data in the schematic, just to give an overall picture of what is being asked and what is being given. This problem is a very straightforward problem in the sense that the initial and final liquid compositions are given. The initial feed is also given. Okay, so we should be able to get the number of moles of residue from direct application of Rayleigh's equation. I did not say that relative volatility is constant. So ln F by W is integral of dx by y star minus x. So this is actually Rayleigh's equation, and then if you have a constant relative volatility, then you can go further and you can get an analytical expression instead of doing this integral numerical. So you can see that the known quantities are F we know, W we do not know. The limits XW and XF both are known, but we need to do this integral. Okay, so for this we need VLE data. So if I know the VLE data, I can actually find y star minus x and then plot it 1 by y minus x versus. So we basically need a plot of 1 by y star minus x versus x, and then you integrate this in the limit of xw to xf. Okay, so then we can obtain this right hand side, and from here we can solve for w. Okay, once I know the w, that's one of the question. The other question is to find the average composite distillate composition, which again we can get from overall mass balance. So this has to be done graphically. So let me also show you the. So if you see, I am taking x values from 0.18 to 0.06 because this is a range of integration that I am interested in. So I am not really interested in data outside this range. So to minimize my effort, I am taking only the x values in this range, and these are the corresponding y values. And this data you can get it from Perry's handbook or any other data book. So we know x versus y, and then I can calculate 1 over y minus x, and then I can plot x versus this function. Okay, then you'll get this kind of a plot. So this plot that you see here is plotted as 1 over y minus x on the y axis and x on the x axis. So here all I need is I need to find the integral of this area under this curve. Okay. So the way I have done is, you can use any numerical method to do this, but the way I have done is I have taken the difference between subsequent points here. Okay. So that will give me the average height, and then I know the delta x. In this case, the delta x is equally spaced. You can see here x is equally spaced at the increment or decrement of 0.02, and then I multiply the average height of this curve times delta x, and then I sum over this area. So I get something like 0.36. Okay. So you can use any other numerical technique to integrate this, but I used a very simple approach here. Problem. So this is 1 by y star minus x, this is x, and this is 0.18, and this is 0.06, and we have obtained the area under this curve. Okay. So that means from this equation, ln of f by w is 0.36. Okay. So from here you can solve for w, and I think you will get something like 70 moles. So you start with 100 moles of the liquid mixture, and then you must have evaporated some 30 moles, vaporized 30 moles, the remaining is 70 moles. Okay. So to find out the average mole fraction of the distillate, so we apply the mass balance. So F times XF must be equal to W times XF plus D times Y average. F is 100, XF is 0.18, W is 70, sorry, this must be XW, this is 0.06, D is nothing but F minus W, so that would be 30 moles into Y average. Okay, and from here you can solve Y average and should get something like 0.46 or something. So this problem is a very straightforward problem. Given the VLE data, inlet, the initial and final liquid compositions, you get the area of this curve, and then you solve for the unknown, that is W. From here you can get D and then Y average. So this is kind of straightforward problem. This is a problem from the textbook. This is exercise problem 9.7 in table. So here you can see that this problem and the previous problem very similar, except that what is given and what is asked are different. Okay, so in this problem, the binary mixture is acetone plus water. Acetone is component A and water is B, because we know acetone is more volatile than water. And this is a differential distillate distilled at 1 atmospheric pressure to vaporize 30% of the feed. So the total feed is not given, only in percentage, so we have to take a basis. Okay, we will take a basis of F is equal to some 100 moles. In this, 30 moles of the feed is vaporized, so D is 30 moles. So from here we know that W should be 70 moles. And what is being asked is, we also know that XF is 0.6. We want to find out what is XW and what is Y average. These are the two unknowns. In the previous problem, this was asked, given, W was asked. Here we have inverted this. W is given, we have to find what is XW. So we'll use again the Rayleigh's equation. So if you see this Rayleigh's equation, on the left hand side we know the value, so it is ln of 100 by 70, and so this integral area under this curve should be equal to 0.356. Okay, if you calculate ln of 100 by 70, that would be about 0.356, and in this equation XF is known, it is 0.6, but we don't know XW. So what we need to do is we need to find XW such a way that the area will be equal to 0.356. Okay, in the previous problem we know the limits, we calculate the area, but here the area is given. Now we need to know which limit of XW will give me this. Okay, so in this problem one of the limit, that is 0.6, is here, and we have to find where the other limit is, so that the area, suppose if I take somewhere here, this area should be equal to 0.356. So this has to be a trial and error method. So you have to choose different XW values, and then you, for each of the XW value, you calculate the area and see when you match it. So what I did was I looked at first 0.6 and 0.5. Okay, so I look at this particular limit. So I assumed, I guessed XW is 0.5 and XF is 0.6. Okay, and I calculated the area of this particular curve, and this area came out to be something like 0.356, sorry, 355. And since this area is similar to what I was looking for here, which is the 0.356, so XW is 0.5. So this is a trial and error method. Okay, you have to use different. So for example, I might have started with X 0.4 and the area would have been larger than what I wanted, so I could have decreased this and then converge to XW of 0.5. So now I know XW is 0.5, then I can use the mass balance. So F is 100, this is the basis we have taken, XF is 0.6, W is 70, XW is 0.5, D is 30, and from here you solve Y average and you get something like 0.833. Then what I also did was, since this range range is very narrow, 0.5 to 0.6, I was wondering if the relative volatility in this range could be constant. So then I can actually use the integrated Rayleigh's equation. So in order to do that, let me go back to the VLE data. So this is my VLE data for acetone water mixture, right? And then this is the 1 by y minus x which I used in the plot, and I calculated the relative volatility for all composition. Okay, you can see it's largely varying. In the very beginning, when it is water rich and acetone lean, alpha is about 50, and then when I go to the nearly about 85% of acetone and 15% of water, the relative volatility is close to 2. So it's a very largely varying alpha. But then if you focus your attention to the range between 0.5 to 0.6, your alpha is not that greatly changing. It is decreasing, but in a very narrow range. So what I did, I took an average of alpha in this range of xw from 0.5 to 0.6, and I got a value something like 4.36. So what I'll do is, in this problem, we have done this problem in a very comprehensive manner, that doing numerical integration everything. But suppose if you know that the range is very small, and if you can check if alpha is constant in this range, which is the case here, I am going to use an alpha of 4.36, and I am going to assume it is constant because the range is very narrow. Okay, so we'll go back here. So this is an alternative idea approach. We say that for x in the range of 0.5 to 0.6, alpha is nearly constant, about 4.36, I think. So with this, what I can do is, then I don't have to do any numerical integration. I can directly use the integrated Rayleigh's equation. So that is ln f by w. So here again this value remains the same as before, and here you have to again, using a trial and error method, you have to use a different xw value and see when this equation is tallied, and you will see that this equation is tallied when xw is close to about 0.5, which is not very different. I mean, it's actually the same value as we got from numerical value here. Okay, and because xw is same, y average will be also the same. So the point I am trying to make here is that even though the VLE can show that the relative volatility can be very different across the composition from 0 to 1, but for a very narrow range, alpha can be considered constant, and whether you do numerically or analytically here, you will get similar results. Okay, so I want you to understand these approaches. So you have to use depending upon how much time you have and how much accuracy you want. Okay, so one of the problem can be that I could just give the entire data, and some of you may just go with the regular method of plotting it and finding area and everything. Somebody who might have thought about this thing would actually think, okay, you know, alpha is very close to same, so you can basically solving it quicker and quicker manner. Okay, so that's the idea of this problem. One catch I would say is that you don't know, actually, unless you do the numerical integration, you don't know the range. Only after you know the range, you can actually check whether alpha is constant or not. So there is a little bit of a convolution here, but what I could do is maybe I can just say that you know, xw will be some range. You know, I can say it's maybe plus or minus 0.2 or plus or minus 0.3. Okay, so, but in this problem, only after doing the numerical integration, we know xw is very close to xf. Then we could check whether alpha is constant in this range or not. Without that, we may not have actually even concluded this. So this is a problem of differential condensation. So generally, there is no question in the textbook or any other resources that I have been following, nor in gate questions. So, but this is something that I set it up based on what we discussed in the class. So, so here we have a saturated vapor mixture containing 40% benzene, 60% toluene, and is differentially condensed at 1 atmospheric pressure. To condense 40% of the feed, compute the composition of the composited residue and the distillate, assume a constant relative volatility of 2.4. Okay, so this is a problem of differential condensation. So that's the key. Differential condensation. So the binary mixture here is benzene and toluene. And if you do not know which one is more volatile or which one is less volatile, I mean, sometimes it's intuitive. We know about acetone, ethanol, methanol. But when you don't know which one it is, usually the first compound will be the more volatile compound. Okay. In doubt, if it's not specifically mentioned, if you don't have a data, you can fairly think that component A would be the first one. Okay. I have not seen any problem where component B was given without further information. Okay. So generally the first component will be A. Okay. And for this particular mixture, alpha is to be set constant to be about 2.4. So here again we will use a basis of F is equal to 100 moles of vapor. Again, recollect, in the batch differential distillation, we start with the liquid and then we partially vaporize the liquid and then we get a condensate and the residue. In the partial condensation, we start with the vapor mixture and then we cool it. Okay, we condense part of the vapor, collect the distillate or the collect the condensate. Okay, so here F, the feed is the 100 moles of vapor, and so we can say instead of XF we will say YF, and this is 0.4. is to condense 40% of the feed. So W is 40 moles. The remaining vapor D would be some 60 moles. And from here it is a straightforward problem because the Rayleigh's equation for partial condensation goes as this. This is something we derived in the class. So once you substitute alpha, alpha minus 1, all the prefactors and all the knowns, you see that on the right hand side the only unknown is the composition YD, and on the left hand side you know. So again, using a trial and error approach, you solve this equation and then you will get YD. This is about 0.5. Now to get the average composition of the condensate, we use the mass balance. So F is 100, YF is 0.4, D is 60, YD is 0.5, W is 40, and from here you solve X average, and X average would be something like 0.25. So this is a problem number 9.8 in textbook. This problem is a little bit tricky, and this involves a little bit of thinking. It is not a straightforward substitution like the previous problems. So take a few minutes to go through this and then tell me how would you go about solving this. This problem is also uploaded in Moodle. So how is this problem different from any of the previous batch distillation problem? Feed is, yes. So operationally it is, so generally if you think about batch distillation or differential distillation, you start with a initial liquid mixture, and then you continue to vaporize. So as a function of time, the amount of liquid in the still will decrease, okay, to the extent that you are vaporizing it. And there are many modifications to this differential distillation. This is one of the operation where you try to maintain the liquid in the still constant by charging with a fresh feed continuously. As much as you take the vapor out, equal amount of liquid you put in, so that you kind of operate under a steady state condition. This is steady state in the context of the flow rates, but in the context of composition, that is not the case. The inlet composition will be the same because feed is coming at a particular flow rate at a particular composition. So feed composition is constant, but if you look at the composition in the still or in the kettle and the composition of vapor, outgoing vapor, that will be continuously changing. So here the question is, how long will the still have to be operated, meaning how long we should continue the distillation before vapor containing 50 mole% of benzene is produced, and what is the composition of the composite distillate. So that means we need to find a way that how the vapor that is coming out of the still is varying with the time, okay, and also keeping in account that this new stream coming into this vessel. So what we actually need to do, we cannot directly use a Rayleigh's equation we derived before, which was the case for batch system. Here now we are changing the operation completely. So we have to go to the basics. We have to go to the material balance problem. Again, we have to write how much moles is coming in, how much moles are going out, what is the accumulation with respect to the total moles, with respect to the species, and then set up a new mass balance equation for this particular problem, okay, and hopefully you will get some expression that will show some time dependence in the composition, okay. So that's the strategy, okay. Part B is very similar, but I will do only part A. Part B you have to do it. The only difference in part A and part B is that in part A the vapor flow rate and feed flow rates are matched, so that the liquid amount of liquid in the still remains constant. But in part B, if you see, I think vapor is generated more than the feed that is compensating. So feed is coming at 15 moles per hour, but whereas the vapor is leaving at 18 moles per hour. So that means you are actually vaporizing more than what is coming in. So over a period of time, you'll have the liquid in the kettle will keep decreasing. It's not a constant level anymore. Okay, so that's the difference between A and B. But I think if you know how to do part A, and part B should be straightforward. Okay, so again I start with the schematic. Okay, so this is my kettle, and this has a kind of a heating jacket where heat is supplied and feed is constantly sent. This is 15 moles per hour with a composition XF equal to 0.4. And the vapor is flowing at 15 moles per hour with some composition Y, which is changing with respect to time. This goes through a condenser and then gets collected into a receiver. Also, initially there is some initial charge is some 30 moles of liquid is present, and the mole fraction there is also 0.4. So we'll do a mole balance for the total material and for species A, in this case benzene. So now how many moles is actually coming in? This is a kind kind of happening continuously with the time. So we have to probably take a small time interval delta t. In that time delta t, you ask what is coming in and what isn't going out. Okay, so I will take small time dt. Okay, so over a small period of time dt, how much moles of the total material is coming into the entire system? When I say entire system, I am talking about the entire system here, okay, including everything. So that would be 15 dt. Okay, 15 moles per hour of charge is fed to the distillation column. So here 15 times dt would be the total moles over that period of time delta t. For species B, for species A, this would be 15 times xf dt, and we know xf, that is 0.4. So this is actually 15 times 0.4 dt, which is nothing but 6 dt. And then moles going out. The moles that is going out is a vapor from the system, that is also at the same flow rate. So we say 15 times dt. And the moles of A that is leaving in the vapor would be the molar flow rate 15 times its concentration Y times dt. And we do not know what Y is, because Y is a changing quantity. At that particular delta t, there is Y. The next time interval, you will have a different Y, okay, because the still composition is keep changing. So now comes this accumulation term. For the total material, it is 0, because whatever is coming in is going out. Okay, so that initially whatever there is present 38 moles, that will remain the same. Okay, for species A, in the still, since L is constant, the only thing that is changing is the composition dx. In the previous problem, I had written d of Lx, because both L was changing, x was changing, but here the operation is done such a way that L remains constant. So dl is 0. So the only change, accumulation term for species A is L times dx. Okay, so now we can write the mole balance or material balance for species A. So moles in minus moles out is equal to accumulation. So that would be 6 dt minus 15y dt is equal to, by the way, L is 30, so I can also put that number here. So I get 30 dx. So then I can write dx by dt is equal to 6 by 30 minus 15y by 30. This is nothing but 0.2 minus 0.5 y. So this equation kind of tells me how the composition in the liquid is changing with the time because of this operation that we are talking about. Okay, and that depends on the composition of the vapor Y. Okay, so this is where the VLE data will have to be used to couple the two. But here in this problem, the relative volatility is actually constant. So we know that Y can be written as simply alpha x by 1 plus alpha minus 1x, and alpha I can be substituted here, 2.51x by 1 plus 1.51x. So I can substitute dx by dt is equal to 0.2 minus 0.5 times 2.51x by 1 plus 1.51x. So let's go back to the question. So what is the question? The question being asked is, how long will the still have to be operated before a vapor containing 50 mole % of benzene is produced? We are talking about not the overall composition of the vapor, we are talking about that instant at time t. You're doing this operation over time some t, we don't know what the time t is, at that particular time t, a vapor is created. That vapor should have a composition of 0.5. Okay, and we know that that vapor will be in equilibrium with the liquid at that particular time, and those are related by this VLE data here. So what I am going to do is I am going to substitute y equal to 0.5, that is a vapor composition I am expecting, and then I solve what should be the equilibrium liquid composition x. So from here substitute y is equal to 0.5 and then find x, and if you do that you will get x to be something like 0.285. Why we are doing this? Because we are getting a differential equation that relates x to t, and I know x initially is 0.4, that is a feed initial composition, that is 0.4. At time t, the vapor that is created should have y of 0.5, corresponding x should be 0.285. So then I have to integrate this equation in the limit x going to 0.4 to 0.285 and time going from 0 to t. Okay, and this is something you can analytically do it. I am not going to show the final expression, but if you integrate this, you will get some combination of terms dx from 0.4 to 0.285. On the right hand side you will have dt from 0 to t. Okay, so you are going to do this integral and then calculate the time, and if you do that you will get t is equal to something like 1.46 hours. And I think Treble's answer was something like 1.466 or something like that. Yeah, it's very close. Isn't that the case? Because x is going from 0.4 to 0.285. So it getting more richer in B, no? Okay, again this problem is not that hard. The only thing is you have to know how to do the material balance for this particular problem. You should know what is coming in, what is going out, do the total balance. So here the total material balance is not a problem because both are same and cancelling. In part B that is not the case. Moles coming in is 15 dt, moles going out is 18 dt. Okay, so there you will see that the total liquid will change, so that you have to take into account. But for this problem it is total level is kept constant, and then you have to worry about only the species balance for A, and then here you can nicely show how the composition will change with respect to time, which is dependent on the composition at time t for the vapor, and now we know how to relate that through VLE data. So now we get a nice expression, and this has to be simply integrated out, and to find the limits the information is already given that y should be 0.5 at time t, correspondingly x can be found out, and then you get this. Okay. Now the second aspect is what is the composition of the composited liquid. Okay, so since we are running out of time, I will just write down the distillate composition. So the mass balance for getting the average distillate composition is a little bit we have to do it very carefully, because you see that we have found the time. You can see up to 1.46 hours how much mass, how much of A we have charged in. That would be 15 times 0.4 times 1.46. 15 is the moles per hour times 1.46 hour. So that will be the total moles multiplied by the mole fraction, which is 0.4. That will give you the number of moles of A charged into the kettle over a period of 1.46 hours. But the still was started with an initial charge of 30 moles containing 40%. So this was also there in the beginning. So this is the total moles of A that has been there initially, and that has been added over a period of time, 1.46. And this has to be equal to how much vapor we have generated and how much A was there. So here 15 moles per hour of vapor was generated times 1.46 hour would be the total moles of the vapor, and then you multiply by some unknown average composition, that is Y average, that is what we want to find out, plus at 1.46 hour the still has a residual liquid of 30 moles, that is constant, but the composition is now different, it is 0.285. This is the final composition of the liquid in the still. So this has to be matched. How much we have put in from this feed, how much was initially there, must be equal to how much is still present in the vessel plus how much vapor has been generated. Okay. In this equation, the only unknown is the average Y. Okay, and the rest you can calculate and you will get about 0.557. Okay. So now if you go to part B has a very similar kind of question. The only thing is the rates, flow rates are different. Okay, so again you have to go back to the basics, do the mass balance, set up the equations, and then you solve this. Okay, we'll stop here.